Okay, so in this section, we are going to learn about Euler's method and how to solve a first order differential equation. Okay, so the first thing is the definition. What is a differential equation? We call it an ODE. And here is the definition. An ordinary differential equation, otherwise known as an ODE, is an equation containing an independent variable x or t and a combination of a dependent variable y and derivatives of y. Okay, so we have the second definition of a first order differential equation is an ordinary differential, first order differential equation contains the dependent variable y and y prime, or y and y prime of x. So you can have a differential equation has a derivatives of y, and y either is dependent on x or it's dependent on t, depending upon how the problem is written. So here are some examples. Okay. So the first three are all first order ordinary differential equations. The first one, as you can see, says that y prime, that is the derivative of whatever the solution is y, is equal to x times y plus x squared. And then they tell you at some initial value of x naught, we can know that y at x naught is equal to y naught. And that gives us a distinct solution to the differential equation. The next example I have is y prime is equal to y times 1 minus y squared. I'm sorry, 1 minus y. So this is another form of a first order differential equation. Again, here in this one, the independent variable is x. And this one, the independent variable is also given as x, even though x does not appear in the problem. In number 3, I have y prime is equal to t squared times y squared. So this one, the independent variable is t. And I need to tell you that the solution at some t naught is equal to y naught. So all three of these are first order differential equations. The last one is a second order differential equation. Y, notice it has two derivatives. So two derivatives of y make it a second order differential equation. 3 derivatives would make it a third order differential equation, etc., etc. So the order is determined by the highest derivative. And notice that for the second order differential equation, I give you 2 conditions, whereas for the first order differential equation, I give you only 1 condition. Okay. Any questions about any of that so far? All right, so the goal of a differential equation is I'm telling you how the function and its derivative relate to each other. And your goal is to solve for the actual function. Okay. So this is what the problem will look like. The problem will look like the derivative of y is equal to some function of x and y, or some function of t and y. So if we go back to the first one, you can see that f of xy so f of xy here is xy plus x squared. For this one, you can see that f of xy is just only a function of y. And if f of xy is only a function of y, then we say it's autonomous. That means y is dependent only, the derivatives of y are only dependent on y itself. So this one is, remember, this one is a function. So this one is going to be f of t and y is going to be t squared y squared. And of course, this is a second order differential equation, so we're not going to talk about it. So this is the form of the problem. All right, so this is the form of our problem, which are going to be first order linear ordinary differential equations. Okay, so here's some examples. All right, so here's the first one. And let's show that this truly is the solution. So here's the solution. This is the differential equation. So the ordinary differential equation is this part. And this is its solution. So we're going to prove that. So y of x is ae to the x. What is its derivative? Dy dx. What's the derivative? We're assuming a is a constant. So what's the derivative of that function? What's the derivative of ae to the x, assuming a is a constant?
Wouldn't it be just e to the x?
Okay, so the constant stays there. So I just get ae to the x. So now if I put dy dx, I get a e to the x. And if I put y, that is a e to the x, I have a true statement. So y of x equal to ae to the x is indeed the solution. Okay. All right, so let's look at number 2. Here's the differential equation. And here's what I'm telling you the solution looks like. Okay, so I'm going to use implicit differentiation to differentiate this. So let's use implicit differentiation. So implicit differentiation says, if I take the derivative of the left-hand side, I'm going to get 2y dy dx. And if I take the derivative of the right-hand side, I'm going to get 2x cubed. So if I divide by 2, I get y times dy dx is equal to x. Oh, sorry, that should be 2x squared. And yes, that does indeed match the differential equation. So yes, that is the solution. That matches the differential equation. So therefore, this is a true statement. So yes, this is the solution. Okay, we have one more. So this says y of x, dy dx minus 2x is equal to 5. Okay, so let's check. So here is so here is the differential equation. And here is what I'm telling you is the solution. So dy dx is 2x plus 5. So now let's put it over here. So for dy dx, I get 2x plus 5. If I subtract 2x, that does indeed equal 5. Again, it is a true statement. So that lets me know this indeed is the solution. So the solution will work inside the equation. Okay. So what does dy dx actually represent? Okay, so dy dx actually is what we say it is all along. It is the slope of the tangent line to the curve of y of x. Nine. This is the slope of the tangent line to the curve y of x. So that means at each point on the curve, at each point xy on the graph of y of x, the slope dy dx is equal to some function of xy at that point. Okay. So now what we're going to do is we're going to use a numerical method called Euler's method to first solve for the differential equation. And then we're actually going to learn two techniques to solve for the differential equation. Okay. So the method we're going to learn is called Euler's method. All right, so here's what we're going to be given. You are going to be given dy dx is equal to a function, and you're going to be given the solution at a particular point, y naught. So I want to draw this. Okay. So you will be given, here's x naught, and you will be told that y at x naught is some number y naught. That's what you're going to start with. Then in small increments of h, which I will explain to you, in small increments of h, we will next find x1. And then we will compute the y value for that, we will call that y1. Then we will compute x2, and we will find the y value for that. We will call that y2. And then we will find x3, and you will compute the y value for that, and that will be y3. And from this, we will get an idea of what our solution looks like. So this is the solution y of x, but we will do it incrementally. Okay. So here's how we actually figure out this formula. I'm going to derive it, even though I'll derive it. Okay. So here's Euler's method. So let's say we're given y of x, then we know y prime of x is the limit as h approaches 0 of y of x plus h minus y of x all over h. Okay, so that is the formal definition of the derivative. So you guys should remember that. All right, so now for the formal definition of the derivative, we're going to assume h is really, really small. So if h is much, much less than 1, that means h is small. Then we can say that y prime of x, we can get rid of the limit and say it's approximately y of x plus h minus y of x all over h. So let's multiply. So we get y prime of x times h is approximately y of x plus h minus y of x. So now when I solve for y of x plus h, I get y of x plus h is approximately y of x plus minus plus h times y prime. But for the differential equation, dy dx, which is y prime of x, is equal to f of x, y. So therefore I get y of x plus h is approximately y of x plus h times f of xy. Okay, so how does this work? So you're given dy dx is equal to f of xy. Let's say I'm given y at x naught is y naught, and they tell me h is given. So I have x naught, x1 is x naught plus h. Go back up to the picture. x1, here's h. So x1 is x naught plus h. x2 is x naught plus 2h. x3 is x naught plus 3h. So I can find each value of x by just adding h. So x2 is x1 plus h, and I keep going. y1 is going to be y0 plus h times f of x naught and y naught, because I know that. So I know x naught and y naught. I can find f at that point, multiply it by h, add y naught. That'll give me y1. And so now I have the point x1, y1. How do I get y2? y2 is going to be y1 plus h times f of x1, y1. And then I will have x2, y2. And as I keep going, I can find or graph the different values of the points, and I will be creating my solution y. Okay, any questions before we get started? Okay. So here's the problem. We want to find, so we're given the differential equation dy dx is equal to y. All right, so in other words, y is its own derivative. So you should already know what the solution is, because we only have one function whose derivative is equal to itself, and that's the exponential. So I expect to get the exponential out of here, or something that looks like it. So dy dx is equal to y. This is a first order differential equation. I'm telling you, when x is 0, y is 3. So the first point is 0.03. So we're starting at 0.3. And I want to get to what y of 1 is, given I know that h is equal to 0.2. Okay. So we start off with x naught is equal to 0. Y naught is equal to 3. Okay, any questions from where we're starting? Okay. All right. So x1 is to add 0.2. So now notice I calculated all my x's already. That was easy. I said, you know what? Every increment is 0.2. So let me calculate my x's. x1 is 0.2, x2 is 0.4, x3 is 0.6, x4 is 0.8, and x5 is 1.0. And that's as far as I need to go, because it says find y of 1. So my approximation y5 will be y of 1. Okay. All right, so now x1 is simply equal to 0.2. Now we have to find y1. All right, so we need our formula. Y at n is going to be y at n minus 1 plus h times f of x at n minus 1 y at n minus 1. Now, in our function f of xy is simply just y. So here it is. Remember, dy dx is equal to f, and in this problem, f of xy is just y. Okay. Okay. Whoops, I don't need that. So y1 is going to be y naught plus h, which is 0.2, and then f of x naught, y naught. Okay, any questions so far? Maybe if I go back and put h in here for a minute before I do that. Let me make that an h. Okay, because I'm using the formula. Okay, so let's see what we get. We get y lower 1 is going to equal, okay, so what's y naught? Y naught, so y of 0 is 3. Plus h, which is 0.2. And then f of x naught, y naught says just put in y naught, which is 3. And that value is 3.6. So now we know y1 is 3.6. Okay. X lower 2, we already said is 0.4. Y lower 2 is going to be y lower 1 plus h times f of x lower 1, y1. Okay, we already know that's going to be y1 plus h times, and know the function value is always to take the previous function y lower 1. Okay, so that's all we need. All right, so let's find it. So y2 says take y1, here's y1. So y1 is 3.6. Plus h is 0.2, and then multiply it by 3.6. And that's 4.32. So now I know that y2 is 4.32. Any questions so far? Okay. X3 is 0.6. Y3 is going to be y2 plus h times y2. So that's going to be y2 is 4.32 plus 0.2 times 4.32. So that's 5.814. Okay, so now we know y3. Now, we're still trying to find the value, the approximate value when y is equal to 1. Okay, so we got to keep going. X4 is equal to, yes.
Yes, it shows that the Y3 is 5.184. Then you
Oh,
put 5.8814.
thank you. Thank you very much. Okay. X4 is 0.8. And Y4 is going to be Y3 plus H times Y3. So that's going to be Y3, which is 5.184 plus 0.2 times 5.184. And that is 6.2208. Okay. All right, we have one more, because then we're there. So X5 is 1. Okay, so that's what we want. We want an approximation for what the Y value is when X is 1. And that's Y5. And that's going to be Y4 plus H times Y4. And Y, so that was 6.220, whoa. 6.2208 plus 0.2 times 6.2208. And that's going to equal 7.465. Okay, so that's our approximation to what y of 1 looks like. So now let's suppose we went to graph this. Okay. So if we went to graph this, we are graphing the following points. 0, 3, 1, 3.6, 2, 4.32, 3. Oh, I am wrong. I am very wrong. We are graphing 0, 3, 0.2, 3.6, 0.4, 4.32, 0.6, 5.184, 0.8, 6.2208, and 1, 7.465. Okay. Three, 4, 5, 6, 7, 8. Okay, so at 0, it was at 3. At 0.2, it was at 3.6. At 0.4, it's at 4.32. At 0.6, it's at 5.184. At 0.8, it's at 6.2. And at 1, it is at 7.4. Okay. So this is an exponentially growing function. Okay, so that's what our guess is for what the solution looks like. Now, the exact solution, so given dy dx equals y, the exact solution with the initial condition, sorry, I have to give you that y of 0. So the exact solution is y of x is 3e to the x. So you get y at 1 actually equals 3 times e to the first power. And 3 times e to the first power is equal to 8.154. So the true solution actually climbs much faster. So actually the true value is up here. So this is error. So we can find out what that true error is. So the error is to take the true solution minus the approximate solution in absolute value. So that's the absolute value of 8.1548. And subtract off, what did we get? 7.465. So that is 0.6898. And then the relative error anybody remember how to take relative error? How do you take relative error?
Isn't relative error like a percentage? So
Okay.
it would be 8.1548 divided by the 0.68.
Okay, well, almost. It's the other way around. You would take the 0.6898 and divide it by the true value, which is 8.1548. And then you'd multiply it by 100. So when I divide that by 8.1548 and multiply by 100, I get about 8.5%. And that's not too bad, but this arrow would go down for smaller h. So if we choose a smaller h, the arrow will go down. Okay. Any questions about that problem? So our goal was to find the approximation for what the solution value is when x is 1. In other words, find y at 1 given h is equal to 0.2. So that's the approximation value. Okay, any questions about that? We're going to do another one. Okay. 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 So now we're starting from scratch, new problem. So if you did not quite understand the first problem, I am very hopeful you will understand the second one. Okay, we are going to use the same technique. All right, so given a differential equation, this time the differential equation is dy dx is equal to 2xy. So that's the differential equation. I tell you when x is equal to 0, y is 2. And we want to find an estimate for y of 2.4. So I want to get down here to find what y of 2.4 is, given h is 0.4. So I can tell from here, x1 is 0.4, x2 is 0.8, x3 is 1.2, x4 is 1.6, x5 is 2.0, and x6 is 2.4. So it is going to take me 6 iterations to get to 2.4 if h is this big. Everybody understand what the task is? Okay, again, we're trying to get an approximation for the solution without knowing the true value of the differential equation. All right, an approximation for the solution. Any questions? Okay. We need our trusty little formula. That is y n is going to equal y at the one before n plus minus 1 plus h times f of xn minus 1 yn minus 1. Okay, so there are a couple things. Can somebody please tell me what is f of xy?
Can you repeat the question again?
What is f of xy? Okay. Let's go back.
Would it be the 2xy?
Okay, good. All right, so remember I said the form of the problem we're going to have is dy dx is f of xy, where we are given y at x naught is equal to y naught. Okay, so the last one we had was autonomous. All right, what do we mean by autonomous? In the last problem we had, the right-hand side, f of xy only involved y, so this was autonomous. Oh, shucks. I don't know why I thought class went to 1:45. I'm moving all slow. Okay, let's speed it up a little bit. We need to get this done. Okay, so f of xy is indeed 2xy. So that means then that our yn is equal to yn minus 1 plus h, and f of xn yn minus 1 is 2 times xn minus 1 times yn minus 1. So now we know our formula. So yn is equal to yn minus 1 plus 2 times h times xn minus 1 times yn minus 1. Okay, so here we go. So the first one, we start off with x0 is equal to 0 and y0 is equal to 2. Okay, so x lower 1, x1 is equal to 0.4. And y1 is going to equal y0 plus 2 times h times x0 times y0. Does everybody see that? So all I'm doing is putting in n is equal to 1 in my formula. And it turns out that x0 is 0. So this whole piece drops out because x0 is 0. So this turns out to equal y0 is 2 plus 2 times h is 0.4 times 0 times and then 2. So that just ends up being 2 again. Okay, so this is 2. All righty. Let's keep going. x2 is 0.8. y2 is going to be y1 plus 2 times h times x1 times y1. So that is equal to y1 is 2 plus 2 times h, which is 0.4 times x1. x1 is 0.4 and y1 is 2. So I get something's wrong. It didn't count that 2, that's why. I don't know why it didn't count that 2, but that should be 2.64. Okay. All righty. x3 is 1.2. y3 is y2 plus 2 times h times x lower 2 times y lower 2. Okay. Y2 is 2.64 plus 2 times H, which is 0.4, that doesn't change, times, now X2 is 0.8, and Y2 is 2.64. Whoa. And that is correct. It is 4.3296. Okay. X4 is 1.6. And Y4 is Y3 plus 2 times H times X3 times Y3. Okay, so again, once I find my formula, I just use it over and over again. So this is 4.3296 plus 2 times 0.4 times X3 is 1.2 and Y3 is 4.3296. So I get 8.4, whoa, not what I got before. 8.586. Did I do everything right? Oh no, this is wrong.
4.3. You put
Yep,
4.4.
I'm getting ready to say I got a different answer last time. That's what I got last time I did this problem. 8.486. Okay. X5 is equal to 2.0. And Y5 is equal to Y4 plus 2 times H times X4 times Y4. And that is equal to 8.486 plus, that won't add. I got to get rid of that. Okay. 8.486 plus 2 times 0.4 times 1.6 times 8.486. 19.3481, that is correct. And then you guys should verify for yourself that the last one is 50.3051. So therefore we can say Y of 2.4 is approximately, that is not approximate. That is the wrong symbol. This is approximate. 50.3051. And that would be the answer to the question. Okay, I never saw, okay. Had a student that asked a question, but he never logged on today, so